Okay, we're in section 71. Contents for you to get through on your own. Examples that I'll go through. I'll certainly have a different take on it than what Wells is doing, but then you get busy with the exercises. My name is Ron Bannon. This is a draft version of my adaptation of Webster Wells' Advanced Course in Algebra, which dates back to 1904. This document, the PDF anyway, is being made available to the participants of the Prison Mathematics Project. All right? So I realize that there may be teachers and students looking at these videos that want access to my document. All right? It's not published yet. It will be published at a later date. If you're interested in receiving more information about that, please consider emailing me. My email address is Bannon, that's B as in boy, the @ NNON.US. All right? Let's go through this over here. Indeterminate linear equations, solutions to indeterminate linear equation with positive integers, yada, yada, yada. Goes through that over there. Read through it. It's a tough read. My take on it a little different than Wells's, but I do want to go through what Wells is doing. All right? So, the way I do something, the way Wells does it, I'm not going to say there's substantial differences, but the thing is, it can't hurt to see multiple ways of doing something. All right? So what I'm going to claim over here is that be careful when you read these things. All right? Now, what I mean by that, if you're reading this equation over here and they want to solve it, right, for x and y, there's a problem over here. They only want positive integers. So what a lot of students will do, they don't read that part, and what they do is they put a solution down to the problem. So let me put out what I mean by that. They write a table down, x and y. They set x to be 0. That certainly is an integer, by the way. But it's not a positive integer, but it's an integer. And then they solve. What do they get? They would get, they would get 5y. That's if x is 0, right? Equals 118. And what do they get? They get 118 over 5 for y. This is not what they asked for. All right? This is not what they asked for. Now, someone said, well, let me try my luck for another one. Let me try to set y to be 0. What would they get? They would get 7x equals 118, and then x would be 118 over 17. I'm sorry, over 7. Not integers, or not positive integers. 0 is an integer, by the way. So I'm going to say over here, it can't hurt to read through what Wells is doing. And basically what I did was I just rephrased it a little bit. All right, so over here, this is, I'll read it through to you. I write the equation down. What I do, I divide both sides by the coefficient on the y. You get the idea. This is what Wells is doing. You could read through that. I don't mind you reading through that. And there's a whole bunch of stuff written down over here. Yada, yada, yada. What I want to get through is what these really are. And the thing about these over here, they're called diaphantine. Now, the Greeks had a field day with these problems over here. And they would be quite challenging when they gave them to their students. And what I mean by that, the integer solutions to the problems were enormous. They're really tough diaphantine equations. What I want to encourage you, though, is that we're not giving you diaphantine equations that are historic in nature, where the solutions are going to be outrageously large integers. All right? We're going to be giving you really simple diaphantine equations. So with that in mind, what I'd like to do is just kind of read this through with you. And it says solving a linear diaphantine equation means that you need to find solutions for the variables x and y that are integers only. And I got to tell you, this is where the crux of the matter lies. Finding integer solution to a problem can be impossible. All right. Now, granted, we're not giving you equations where there's going to be an impossibility of finding integers, but let's keep reading through it. All right. Now, there may be further restrictions placed on the integers being positives. But all I can say is this: if you're finding integer solution to a problem, we can march our way towards the positive integers. We can always do that, all right? So what I want to do is, let's talk about how to do it, all right? So I'm going to say it's more difficult than standard solutions where you're setting x to be 0, y to be 0, and getting fractions. We can't deal with the fractions now. So I'm going to say over here, the technique, right? It says you must first find the greatest common factor of the coefficients in the problem, and then use the result to find a solution. All right? We'll go through examples, by the way. We'll go through the same example that Wells went through. If you can find one integral solution to an equation, you can apply a simple pattern. And again, I'll tell you what the simple patterns are. And by that simple pattern, you'll be able to find infinitely more integral solutions to the problem. For example, if we noted that x rises by 5, we'll go through how I know that, and y declines by 7, I can march towards any solution to the problem, and we will go through that. All right? So let's outline what we're looking to do. All right? So it says A, and we'll go through the steps, by the way. Write the linear equation in standard form. The standard form is this form over here. AX plus BY equals C, where A, B, and C are integers. You should reduce the equation if there's a common integer factor between A, B, and C. What are we trying to do? Reduce the size of the numbers if we can. Okay, next up, B. And we'll go through an example. Find the greatest common factor of the coefficients in A and B. If the GCF of A and B divides C, then you know your equation has an infinite number of integral solutions, and that's good news, by the way. If the GCF of A and B does not divide C, then you know your equation has no integral solutions. All right, C. Solve AX plus BY equals C for Y, and use your head. This is the part where a lot of people say, I have to use my head? Yeah, you got to use your head to find an integral value of the variable x that makes y an integer. Once an integral solution is found, you're going to use the ratio minus a over b to generate more as you like. And we'll go through this. All right, so let's take a look at our example. And the example that we've been given, I want to point out the same examples Wells started with. My work is going to look a little bit shorter than his, but I can't say it's better than his. I would never say that. What I'm saying is my work to do the problem. I do appreciate what Wells is doing, but I'm going to do my method. Just like what you say, I want to try my method. And by the way, there's other methods besides what we're showing you, and certainly there's other methods. So the first thing I want to do is just go back and read it, and I want to make sure it's in that standard form. And the standard form is AX plus BY equals C. I definitely see that. Here, A and B and C are integers. I clearly see that. You should reduce the equation if there's common integer factors between A, B, and C. Well, what I noticed that there are no common factors between 7, 5, and 118. All right, next up, find the greatest common factor of the coefficient A to B. Let me write this down for you. What's the greatest, whoops, sorry about that. What's the greatest common factor between 7 and 5? Well, that would be 1. All right, so on step number 2. If the GCF of A and B divides C, you now know your equation has an infinite number of integer solutions. So now I know there's an infinite number of solutions that are integer pairs. I just don't know what they are yet. All right? So next thing they say is that you should probably, I should say probably, we're going to follow the instructions. You should solve the equation for y. So let me put that down for you. I'm going to solve this for y. Now again, you might say, is this going to work? Well, I know there's integer solutions, but they may be so difficult I can't find them. But I'm hoping not. So what do you get? We're going to solve for y. So you get 5y equals 118 minus 7x. You get the idea what I'm doing? Then I'm going to divide by 5. And what do you get? 1x minus 7x over 5. Again, I hope I didn't go so fast you couldn't follow me there. All right, now, do I see that written down over here? I do. It's right here. Now, I realized last time I was looking at it, I don't think I could do it. Well, I got to be honest with you. I think they're going to be manageable integers. Now, what I mean by that, if you're just simply, thuggishly going through it, I got to find a number on top that's divisible by 5. And I'm going to try numbers. I'm going to try, like x is 1. Now, this might seem like craziness to you, but if x is 1, what do you get? 111 on top. That's no good. Right? Let's try 2. What do you get on top? 118 minus 14. Again, I'm looking for a number by 5. 5's not that bad, right? So what do you get over there? You get 104. That doesn't work. I'm going to try x is 3. Now, someone says, how many do I have to try? Well, if this were a Greek linear Diophantine equation, this would not be a good technique. All right, let's try that 3. What do you get? 118 minus 21 Well, I know I get a 7, so I'm going to say that doesn't work either. What I mean by 7, the first digit would be a 7. Let's do the next one. X is 4. And I'm starting to see it now. 118 minus 28 is going to be what? 90. So I found something. I'm going to say an x is equal to 5. I found a number for y. Let's write that down. So it's 118 minus 35, right? 5 times 7 is 35. Oh, I'm sorry. I said 4, and I wrote 5 down because 5's not going to work, and I apologize for that. Let me get this eraser out. Again, I said 4, and then I wrote down 5, which is crazy. 4. Then you get what? 118 minus 28 over 5. Well, that's going to be 90 over 5. And that's going to go in 18 times, right? So I found one integer solution to the problem. What's that going to be? 4, comma, 18. If you want, you can check it. And if you're going to check it up here. 7 times 4 is 28. 5 times 18 is 50 and 40, which is 90. 90 plus 28 is 118, which is exactly what they said it was. All right, now someone says, how do you generate other ones? I don't want to go through this guessing game again. It's over. I'm not going to do that again. What I'm going to do, though, is I'm going to rewrite this thing over here in a simpler way. All right, so I'm going to write down y is equal to minus 7 fifths of an x plus 118 over 5. Now what I'm going to claim over here is this is the number that's going to allow me to march towards a solution in the problem. And what I'm going to do is I'm going to put a table down over here, and I'll tell you how I'm going to march forward. And we're going to check them. Remember, I'm still going to check x and y. I have one solution. It's 4, comma, 18. And I can generate an infinite number of integer pairs that will satisfy this by using these numbers here. What I'm going to claim is, I'm looking at this, and this is going to be the change in the y's. I'll write this down for you. That's the delta y. That's minus 7. And the delta x is 5. Well, let's do that. So I'm going to go up 5. What number would you get? 9. Now I'm going to do this, which is down by 7. What would you get? 11. So now I'm going to claim 9 and 11 is also an integer solution to the problem. Let me write that down for you. And I can generate as many more as I want. What do? Back to the original. 9 times 7 is 63. Plus 5 times 11 is 55. 63 and 55 is going to be 110, 118. By the way, you shouldn't be shocked. Could I get another one? Of course I could. What would you do? Keep going up by 5 on the x's. What's 9 up by 5? 14. I got to go down 7 on the y's. What number would I get? Let's see, 11 minus 7 would be 4. Let's check it. I'll write this down for you. 14, comma 4. Let's check it. Well, 7 times 14 is going to be 70 and 28, 98. And 5 times 4 is 20, and 98 plus 20 is 118. It works beautifully. Now, again, you can keep moving if you want. Now, if I keep moving, what's the next one going to be? Well, if I go 5 up from 14, I'm at 19. But here's what happens. If I go down 7 from 4, I'm in negative space over here. But it's still an integer solution. They're just not positive integers. And what would you get over there? You get minus 3. Does that work? Yes, but it's not what I wanted. Now, if I did this one over here in the other direction, you could do that too, but I got my 3 integer solutions over here. Now, let me go back to the question. And what did they do? Solve in positive integers. Well, I found them. All right, what are they going to be? These 3 guys over here. These are the only 3 ordered pair positive solutions that work. Are there other ordered pairs? Yeah, but unfortunately, they're going to have negative numbers in it. So let me go to the picture. The picture is of the line. What line is this? The line is, I guess to remind you, the line is 7x plus 5y equals 118. And we got our integer pairs over here. Let me point them out to you. And again, we give you a visual for you to look at it. What integer pair do we have here? I'm looking at it. I'm going to say it looks like, let's see, it looks like 14.4. And this one over here looks about 9.11. And this one over here looks about, let's see, what number does that look like to me? 4, 18. I hope you realize what I'm doing over here. I'm kind of analyzing this thing. And sometimes if you drew a really good line, could you see those? Yeah, there's a good chance you could. What's the problem? Most people can't draw good lines. I'm just tracing over to make sure you know I'm seeing these points clearly. Who's drawing the line? Computer is. Computers do integer problems? Yeah, they're really, really good at it. I want to read the rest to you, though. The rest says moving forward from the point 418, you get 911, 14.4. Yeah, we did that. Although I appreciate what Wells does, I prefer to do it differently. However, to solve a linear differential equation gets more involved with integral solutions are big. And they're really not going to be big here. They're going to be kind of reasonable. Big, of course, is a bad word in mathematics because it's not precise. And big to you may mean small to me and vice versa. Again, we don't use words like big and small in mathematics. It's not a precise term. An accurate graph is provided. I like to provide a graph for you to look at. And part of that's a learning curve, all right? Now, someone says, I wonder if there's other integer solutions to that. There's an infinite more, but these are the only 3 positive integer solutions. The other ones are going to have negative coordinates in them, all right? Now, I'm not saying they're not going to be, both negative. One will be negative, one will be positive, but they're not both positive, all right? Let's look at this one over here. And again, by looking at it, I'm looking at it, and someone says, I can't remember what you've done. Well, I'll explain to you what we've done. We look for the GCF. I'll write this over here. Between 8 and 13. And by the way, this is written in standard form, by the way. And what's the GCF there? It's 1. And 1 certainly divides 100. So I know there's going to be an integer solution to this problem over here. So my problem now is like, if there's an integer solution, can I do it? All right, now I'm not worried about the positive part yet. I'm just worried about getting an integer. And what was the suggestion over here? The suggestion was to solve this for y. That's a suggestion, by the way. So let's take a look at that. What would you get? 8x minus 100 equals 13y. And I can solve that for y now. Write this over here. Y equals, and I'm going to write down, looks like 8x minus 100 over 13. Now, you may wonder what I'm going to do now. These numbers are kind of big for me. I'm just going to maybe factor it, all right? So I'm going to put y, and I'm going to put down a 4, because it makes it easier for me. And you get 2x. They're smaller numbers now. Minus 25. Let me just check I'm doing that right. 4 times 2x is 8x. 4 times 100. Now, I clearly know that 4 has nothing in common with the 13. So what I'm looking at a very small number here, this guy over here, and I want to try to make that divisible by 13. And again, you could play around with it. I'm not saying you can't. So I'm going to say over here, I don't know, let's say you chose 1. Now, if you chose 1, I'm just looking at this. What would you get? Well, 2x minus 25, and I don't care if it's negative or positive. I'm just wondering, can I get a divisor? But unfortunately, that's going to be what? Minus 23, right? That's not working out. Let me try 2. What would you get there? 4, that's 21, minus 21. That's not working either. Let me try 3. What would you get? That's minus 19. That's not working either. Don't give up, though. It's very simple numbers. Let's try 4. Right? What do you get there? 2 times 4 is 8. And 8 minus 25, I'm sorry, I did something crazy there. I'm daydreaming again. I said x is 4, right? And what would you get? 2x minus 25. That's 8 minus 25 is 17. That's bad news, too. Let's try again. Don't be discouraged. Get 15. Let's try 6. That's 12. 12 minus 25. Wow. 12 minus 25 is minus 13, right? This is good news. So I'm going to say, you know what, it was a little bit of marching. And, certainly the more I march, the easier it gets for me. Sometimes I do make mistakes, by the way, but I found a solution now. And I'm going to write it down for you. I found x is 6 works really nicely. I'll check it still because I can still make mistakes. So if x is 6, y would equal, let's write this down for you. X is 6, you get 12. 12 minus 25 is minus 13. Minus 13, 5 by 13 is minus 1. So y would be minus 4. All right, so someone says, if you found one integer pair, and I did, I can use the pattern to find others. And I want to put down what the pattern is. The pattern is going to be this. It's y. Again, we're still looking at this over here. And I want to write down the pattern for you. Y is 8/13 of an x minus 100/13. It's this thing I'm looking at for the pattern. And let's write this down now. And I'll put it in tabular form for you. All right, tabular form. All right, so the table is going to look like this over here. 6 minus 4. No, they're not positive. So what am I going to do? Well, the delta y is the 8. And we'll check whatever we say. The delta x, this is the change, is 13. Let's do it. Let's start counting. So let's see. If you're at 6, you go up 13, you're at 19. If you're at minus 4 and you go up 8, you're at 4. This is one integer pair where they're both positives. Let's do the next one. All right? Now, if you're at 19 and you go up 13, where would you be at? Well, that would be what, 32, right? If you're at 4, you go up 8, you're going to be at 12. Now, by the way, I hope you start to realize there's going to be an infinite number of integers, pairs, that are positive. What's the next one going to be? And I want to keep going there, but the next one's going to be what? 45, and then 12 up 8 is 20. I just want to tell you that I know they keep going up and up and up. They're always positive. Now, someone says, could you keep writing them down? Of course you could, but you got to stop at some point and realize what you got over here. So what I want to claim over here is that I found some solution to the problem. But you know what? I'm always saying, can you check it? And I want to check these for you. All right? I know it's tough, but the first point I want to check is 19, 4. We'll look at the key later. What do you get? What's 3 times 19? I'm sorry, 8 times 19. Well, I'm going to write this down for you. It's going to be, and again, what I do it might be different, but 8 times 19 is going to be 80. And then 8 times 9 is 72. And then it's minus 13 times 4. And that's going to be minus 40, and 12 minus 52. Does that equal 100? I don't know. Well, 72 minus 52 is 20, and 80 plus 20 is 100. So that works. What's the next one? And it's tough. 32, 12. Let's put it down. What's 8 times 32? Oh, it's going to be a tough one. 8 times 30 is going to be 240. 8 times 2 is 16. 12 times 13. All right, write this down for you. 12 times 13. Well, it's going to be 120. Right, 10 times 12 is 120. And 36. So it's going to be minus 156. Well, let's see if you can do that. That's 240. No, 256, I'm sorry. Minus 156. That equals 100. It's working out beautiful. Now, granted, you could do the 45, you could do the 20, but they'll all work out, all right? So I'm going to write my 3 pairs down. I'll put them down for you. This is a nice, whoops, I did it again. This is a nice ordered pair. We checked it. This is a nice ordered pair. We checked it. This is a nice ordered pair. We didn't check it. But your bottom line is, if you write down 2, you really got the pattern. And let me take a look at it, see if I wrote them down for you. I put the 19.4 down. And by the way, I just wrote the pattern over here, where n is an integer. That would generate all others, by the way. Let me look at the picture. I want to point out, looking at the picture, I want to, again, when I'm pointing out the picture over here, you can blow these things up over here. Looking at this thing over here, clearly when I blow it up, I see that 19, 4. And over here, clearly when I blow it up, I see the 32. and the 12, all right? So let's put this over here, and let me make sure you got that. You got those two over there. Now, someone says, I don't see the 4520. The reason being it's over here somewhere. I just don't see it. Now, you can graph it out if you want, all right? So I mentioned the reason integer problems are so interesting to us is that, the world is composed of integers. And a lot of times they're just, the solutions to problems really don't involve fractions. They involve integer values, all right? So what I want to do is I want to read number 3 to you. It's a word problem. And I know that there's $14.40. But then their question is, in how many ways can the sum of 1440 be paid with dollars, half dollars, and dimes? Dollars, half dollars, and dimes. Well, you know what? I'm going to write everything down as an integer. And an integer for $1 would be 100. $1 worth 100. Now, let me just get a pen out. So it's going to be 100, and X would be the number of dollars. And let me write this over here. What are half dollars worth? 50. And I'm going to say there's Y half dollars. And then dimes are worth 10. And how many dimes there are? I'm going to say Z. And how many pennies would I have in the end? 1440. Okay, let's keep reading it. Now, I want to point out, I'm reading something over here. I better understand what I'm reading. It says the number of dimes being equal to the number of dollars. Well, maybe I didn't write this stuff down, but maybe you understand what I'm doing over here. So the number of dimes is equal to the number of dollars. Now remember we said X is the number of dollars and Z is the number of dimes. Well, I can rewrite this equation now. What do I get? I could write 100X plus 50Y plus 10, Z is equal to X, right? 10X, 1440. Well, did they say anything else? No. Oh, wait a second. Did I write that right? I'm sorry. I didn't read it fully. I got to go back and erase it. And that's my problem. I didn't read it fully. Sorry about that. The number of dimes, and I really apologize for not reading it fully. The number of dimes, which is Z, is equal to the number of dollars and half dollars. So the number of dollars is X, the number of half dollars is Y. And I apologize for not reading that sentence completely. All right, let's write it down again. It's going to be 100X plus 50Y plus 10, and what's Z equal to? X plus Y. I got to simplify this. 100X, 50Y, plus, 10X plus 10Y equals 1440. Boy, it's going to get tough. You get 110X plus 60Y equals 1440. Well, I got problems here. I want to point out, I'm going to divide by 10 first off. You get 11X. I need to make the number smaller, by the way. Plus 6Y equals 144. All right, now, by the way, I'm not going to say you can solve an equation like this for integers, but I want to go through that technique we're looking for. And what am I looking for? I'm looking for the GCF, because I don't want to go forward on this unless this happens. What's the GCF between 11 and 6? That's 1, and 1 goes into 144. So we're good to go. So what are we going to do? We're going to solve for Y. Let me write this down for you. So Y, or 6Y, would equal 144 minus 11X. And now I got to divide by 6. Well, I'm kind of running out of room, so I'm just going to divide by 6. All right, this is the problem now. And I know it's a problem. The problem is, students can say, can I do that? Well, here's the deal. You've got to pick an X integer that's going to work out. You must produce an X integer that's going to work out. Now, someone says, why is that? These things have to be in integers. You can't have half of a dime or something like that. It's just not possible. You can't have half of a dime. Although somebody say you could have a nickel then. No, they don't have nickels. They're just dimes. There's either 1 dime, 2 dimes, 3 dimes, 4 dimes, yada, yada, yada. So I know these numbers have to be integers. So then the question is, well, what are you going to do? And I'm going to tell you something over here. You know, I'm looking to do something, right? And immediately what I notice I got something that's pretty simple. And I'll write it down for you. And so why does that look simple to you? If you just choose x to be 0, right? If you just chose it to be 0, what would you get? You would get 144 over 6. And by the way, 0 is an integer. This is good news, by the way. I don't know if this is going to work out, but what would you get? You would get 72, dividing by 2, by the way, over 3. And does 3 go into 72? 20, right? That's 60, and then you get 24 times. Is that agreed? So I'm going to say y is 24. So someone says, what are you going to do now? Well, I'm not saying that's the answer. What I'm saying, that's a pair of integers. And write this down for you. And then I'm going to look at this equation over here, and I realize I got something pretty simple. I got what? 24 minus 11/6 of an x. Let's go through this. The delta y is this number here. And the delta x is going to be 6. I'm going to start marching toward the solutions now. By the way, I'm no longer thinking about the problem. What's the next number going to be? 6. Well, if you're at 24, go down to 11, you're at 13. Let's keep going. If you're at 6 and you go up 6, you'd be at 12. If you're at 13 and you go down 11, what number are you at? 2. Now, by the way, I want to point out, these are the only ones making sense to me at this point. Could you go on? No. Why is that? If you go down 11 from 2, where would you be? You'd be in negative territory. So now I'm going to say I have 2 different solutions to the problem. All right? So I'm going to write this down. I want to see if it makes any sense. So I'm going to say x is 6, and I'm going to say y is 13. Now, what does this mean? And I got to be real careful about this. This means that z is this thing over here. And what's x plus y? 19. Now, granted, maybe I didn't write everything down for you, but x is the number of dollars, right? So I have $6. And then y is the number of half dollars. And what would that give me? Well, 13, that would give me what? That would give me 13 halves, right? And 13 halves is going to be 6.5, right? We're just checking. And how many dimes do you get? We have 19 dimes, which is 90 cents. $1.90. Let's add it together. You get 0. 9 and 5 is 14. 6 and 6, 12. Let's see, 13, 14. We got this. So that's one answer. I want to point out where that answer is. We write down in English. $6, 13 half dollars, and 19 dimes. What's the other solution we found? 12 and 2, right? I'll put this down. And what's C? Again, I can't say it enough times. It's x plus y, which is going to be 14. What does this give me? Well, x is the number of dollars. That's $12. 2 is the number of half dollars. That's going to be $1. And 14 dimes worth of $1.40. What do you get? $14.40. So what am I going to say? I'm going to say $12 coins, 2 half-dollar coins, and 14 dimes. All right? It's tough, though. I know that. But I want to assure you, though, that these are linear Diophantine equations. You should verify that. And the integer solution is going to be kind of small. All right? What does that mean? Trial and error is going to work. Right? Is it going to work on really large numbers? No. It's going to work over here. So what do you have to do now? You've got to do the exercises. So I want to point over here. He likes to use the positive integers. That's a linear Diophantine equation. The GCF between 3 and 5 is 1. That certainly divides 29. And we do the same thing we did before. Right? Linear Diophantine. There'll be integer solutions, though. That's what I'm telling you. Linear Diophantine. The GCF between 6 and 29 is 1. Certainly divides 274. So forth and so on. All right. Are the numbers getting a little bit more challenging? Yeah, a little bit, but not substantially so. They're not huge numbers. Remember, the Greeks had these huge numbers that they were giving their students. These things are quite manageable. Now, again, if you're looking at my work and saying, you know what, I want to do what Wells is doing, you're still going to get the same result. It's still the same amount of thinking involved, but the bottom line, it may look different to you. It's really the same technique, but there's a lot of things over here. I hope you realize that. All right, a lot of questions that you do. 13, 14, ooh, 15 looks tough. I want to point out, I would definitely do elimination first, by the way, because I don't want to do a 3-variable system. And to do that, you know, what would I eliminate here? Probably the z. Now, once you do that, you're going to get an equation which may or may not be a linear Diophantine. My suspicion is going to be a linear Diophantine. So eliminate the z and then proceed forward. Again, this may be a stretch in reasoning. However, I want to put work down for you. Same thing. Get rid of one of the letters, and you have a linear Diophantine equation. This is a money problem. Money problems are typical Diophantine if they're correctly written, by the way. And that's 17, 18. Ooh, 18's tough. I want to point out why it's tough. They're using symbols you may not be aware of, but there's a footnote over here. There's a footnote. Again, if you're confused by these things over here, you can always skip things. I found this problem to be challenging myself. I had to look things up. I did not know what a half crown was, yada, yada, yada. I had to look things up, and that was a problem. I had to look them up. When I look them up, basically, I had to look things up. I'm not in the British system. By the way, Wells was an American, but Wells traveled to Europe, and he certainly became familiar with the European system. I think he was an alpinist, and he went to, I guess he must have had money, by the way. He went to Europe and enjoyed himself for a while. And I think he tried to get a PhD in Europe because PhDs were really hard to come by in the United States, but the Europeans were well ahead of the Americans at that point. So the deal about this over here, there's 20 more money problems. There's plenty of, there's a farmer with pigs, sheep, and calves. They got to be integers, by the way. I hope you realize that. And it's interesting that you can solve these things. More money problems. And we have, there's 22 questions. Let me repeat this. This took me time to get through as well. It isn't something I look at these and say, this is easy peasy lemon squeezy. It's not. All right, Sage. Sage is quite capable of doing equations. It's also capable of doing what's called linear programming. I didn't do that over here, but it's capable of doing linear programming. And linear programming is a whole area of mathematics that some people are quite good at. And what do I mean by that? Linear programming are problems that have linear solutions at lines, but they're going to be, typically they look for integer solutions to their problems. Not always, by the way, but integers are nice to come up with. All right, so I come over here is that, get into the Sage stuff over here. That's what we're talking about, the Sage business. What's Sage? It's a computer algebra system, CAS for short. It's open source. Go to this website, you can download or interactive web-based application. We're really not teaching Sage over here. What we're trying to do is get you to do the problems as Wells would want you to do the problems by hand. Again, if you think there's an error, and I'm not beyond making error, please reach out to me. My name is Bannon. My email address is also Bannon. That's B as in boy, the @ symbol, NNON.US. And please feel free to reach out to me. Thank you.